Okay, so today I'm gonna be going through all the tutorial 2 thermodynamics problems. So let's go ahead and start over here with problem number 1. So we need to estimate how long it will take to bring a cup of water of 250 milliliters to boiling temperature in a 600 watt microwave. So let's start by writing down what sort of information we have and which information we don't. Let's see. So we know that the volume of the water is 250 milliliters, which is the same as 250 times 10 to the minus 6 cubic meters. We also know that the power of the microwave, let's say work flow, is 600 watts. We have a starting temperature of T initial 293 Kelvin. We need to first explain why there is no heat involved in this process. So if you think about it, when you put something in a microwave, the microwave uses electromagnetic radiation, microwaves in this case, to sort of excite the water molecules inside the food, and this is what actually causes the increase in temperature. As we saw in class, well, during the tutorial, we saw that C delta T was equal to the heat transfer and the other work done. In this case, even though Q here, so there is no direct heat transfer, even though this is 0, we still have work being done by the microwave onto the cup of water in this case, in the form of radiation. And it's this radiation that actually causes this change in temperature. So now that we've gotten that out of the way, let's try and find the actual time that it takes to heat this cup of water up to boiling. We know that, well, we know Q is 0, so we can skip this for now. Let's say we need to find what work is being done. So let's start by figuring out how much energy the cup of water actually gains. So we know that the change in internal energy will be the heat plus whatever work is done on it plus the boundary work. Now, assuming that none of the water evaporates, of course, your water stays in the glass, so the boundary doesn't change, which means this is 0. As we've established already, there is no heat as well, so that means that our change in internal energy, delta U, is equal to simply the work of the microwave, which in this case is the other, whatever remaining work, right? Now, we know that this is equal to Cp delta T. Now, we do have delta T, even though we were just given the initial temperature, we are told that this has to come up to a boil, and boiling temperature for water is 100 degrees C, which is the same as 393 Kelvin. If you say that, the conversion rate is 273. So we now have that our work is equal to the mass, which we weren't given, but we have got the volume, and using the density of water of 997, I believe, kilograms per cubic meter, we can calculate the mass, because mass is simply density times volume. So we have 997 times 250 times 10 to the minus 6, and this will be kilograms, times our specific heat capacity, which, if you look it up, is 8.316 kilojoules per kilogram Kelvin. So I suppose we can write this as kilograms. And we have our change in temperature. So our final temperature is 393 minus, wait, no, I made a mistake here. It's 273 minus 293. So if you plug all these numbers into your calculator, you get a total energy of 83,266 joules, which, for simplicity, I'm just going to write as 83.266 kilojoules. Now, we need to calculate the amount of time that it will actually take for the microwave to basically do all this work on the thing. And the good thing is that we've got the work rate. So our work rate is 600 watts, which is basically 600 joules per second. So the time it will take for this water to heat up to a boil in the 600 watt microwave will be the total amount of energy that we need, which is 83,266, divided by 600 watts, which gives us 138.78 seconds, which, if you divide by 60, so divide by 60, you get 2.31 minutes, which, if we look over here in the thermodynamics problem, over here, we indeed have 2.3 minutes as the correct answer. So, problem 2. We've got an insulated rigid tank filled with helium. So, first, what I like to do is I like to draw the situation. So, we have a nice little insulated tank over here. I'm gonna draw the insulation around it simply as a larger square, basically. And we've got a shaft into here. And this shaft seems to have a power rating of 10 watts. So let's say workflow shaft is 10 watts. The time it's running is 30 minutes. We are also told that our insulated tank initially contains half a kilo of helium, so mass equals 0.5 kilograms. We know that T initial is 25 degrees C, and P initial is also 1 bar, which is 100,000 Pascal or 10 to the 5 Pascal. And this in Kelvin would be 298 Kelvin. So I suppose step one for this problem would be to find our internal energy again. Now, there are a couple things that are nice about this. First of all, it's insulated, so we know that our heat flow will be zero because there can be no heat flow between the inside of our box or our tank and the outside. That means that Q dot equals zero. And we also know that the volume cannot change because it's a rigid tank, which means that only the pressure increases, not the volume. This makes some stuff easier. So let's start by finding, as before, the change in our internal energy, which, as we said, is Q plus work other plus work PV. However, this volume doesn't change, so it's zero, and this, it's insulated, so it's also zero, so it's once again only equal to the other work. Now, work other here, we can figure out what it is because the only other work is being done by this shaft, so we know that it is running at a power of 10 watts for 30 minutes, so 30 minutes is the same as 60 times 30, which is 1,800 seconds. So 10 watts for 1,800 seconds, which is 18 kilojoules. Then we know that our internal energy for an ideal gas here, well, U equals F over 2 nRT, or let's do delta U, so this will become delta T, and this will become mCV delta T. So now all these delta T's can drop out, which leaves us with F over 2 equals, NR equals mCV. This should be small c. And what you will notice here is that N is equal, so the number of moles is equal to mass divided by the molar ratio, which is, so this gives us F over 2, it's a terrible F, over 2 times R over the molar ratio is equal to CV. So what I did here is I replaced N with this expression over here and then divided both sides by M to get our CV. So now we need to figure out what the molar ratio for helium is. So for this, we're gonna actually go ahead and have a look at our periodic table over here. So if we look for helium, it's over here. This should be straightforward actually. We know that it's a monoatomic gas, which already tells us F. So F should be 3. And we can see here that its mass is just about 4 grams per mole. So Let's go back to our to the worksheet here. So helium is monoatomic, which means F equals 3, and the molar ratio is about 4 grams per mole. We just need to plug this in, so we get that CV. If you plug in the numbers into here, we get 3 over 2 times 8.314 over 4 times 10 to the minus 3, because remember it has to be in kilograms, which gives us a nice little number of 3,117.8 kilojoules per kilogram per mole. Per Kelvin. Okay, so now that we've got our CV, we can go ahead and calculate our final temperature. So we know that delta U equals mCV delta T. So therefore delta T must be equal to delta U over mCV. So delta U from the beginning we know was 18 kilojoules. Divide this by the mass which we were given, so 0.5 kilograms. Multiply this by our CV, which we just calculated. This is in kilojoules per kilogram Kelvin. So you can see that here kilojoules and kilograms will drop out. So we get that T, our final temperature, minus our initial temperature, is equal to 11.6 Kelvin. Our initial temperature was 298, so we just need to move Ti to the other side, so we get 11.6 plus 298, which is equal to 309.6 Kelvin, which is equal to 36.6 degrees C, which if we look at our tutorial sheet, okay, we were 0.1 off, so there's probably a rounding error somewhere, but it's fine. So this is the answer to A, and now we need to do part B, where we need to show the final pressure of our helium gas. So let's go ahead and do this with the ideal gas constant, or the ideal gas law, So we have PV is equal to nRT. So here we have all our initial temperatures, and well, the volume doesn't change actually because we have a rigid container. So let's start with this. So we have two different situations. So we have our initial pressure with the volume is equal to nRT1, and we've got our final pressure times the volume equals nRT2. Or let's be consistent, T initial and T final. So from this we get that nR divided by V is equal to Pi over Ti, which is also equal to Pf over Tf. And the reason for this is, remember, volume is constant. N is a constant because there's no gas escaping the thing. We know it's sealed. And R is a constant anyway. So that means that everything on the left side is a constant, and that means that everything on the right side must also be constant. So these two ratios are equal to each other. And from this, we can calculate our final pressure. So if we simply do a bit of rearranging, we get that final pressure is equal to initial pressure times the ratio of your final over your initial temperature. And now it's just a case of plugging in the numbers. So our initial pressure was 1 bar, so 10 to the 5 Pascal. Our initial temperature was 298 degrees Kelvin, and our initial was 309.6, which gives us 1.0386 bar. And I'm gonna assume this is also slightly off. Yeah, it's one. Yeah, it's one value off, one figure off. So honestly, I think it's just a rounding error somewhere. So I think it should be fine. And now finally, we are also asked to draw this on a PV diagram. So let's go ahead and do that. So here we've got our pressure in bar, and here we've got our volume. So we know that our volume doesn't change, so that already straight away means we're just gonna have a straight vertical line between our initial and final pressure, and it's just a case of labeling it. So our initial pressure was 1 bar and our final pressure was higher, which was 1.0386. And yeah, this is the PV diagram. We can see that as it's just a vertical line, there is no area under this line, which is consistent with there being no boundary work, because again, our box didn't expand. So that's nice. Let's move on to problem number 3. So problem number 3, we have a piston cylinder. So let's go ahead and draw that. So this is gonna be my piston head, and I don't know, probably has a shaft attached to it. Okay. It initially contains 0.5 cubic meters of nitrogen, so the initial nitrogen equals 0.5 cubic meters at 4 bar, so P initial equals 4 bar, and it is at 27 degrees, so T initial equals 27 degrees C, which is equal to, here we're going to be a bit more precise, so let's use a conversion rate of 273.15 degrees. So this comes out to 300.15 Kelvin. What else? An electric heater within the device is turned on. Okay, so we've got an electric heater. I'm gonna assume it's just some sort of resistance that dissipates heat into the volume. It has a current of 2 amps. It runs for 5 minutes. So 5 minutes times 60 is 300 seconds. And then we have a voltage. Okay, let's differentiate the V and say voltage source is 120 volts. It expands at a constant pressure, so we have constant P, which means P initial and P final is the same. We do have a heat loss of 2,800 joules, so let's say Q loss equals minus 2,800 800 joules. And the reason I put a minus here is because, according to our convention, energy going into a system is positive and any energy going out is negative. So therefore, those 2,800 joules that we lose is negative. So what do we need to find? We need to determine the final temperature. So we need to find TF. And we can assume that nitrogen is ideal using R equals 8.314 kilojoules. Oh, no, joules per mole Kelvin. Okay. Okay, let's start by working out how much energy or how much work this heater is actually doing. So the workflow of the heater, you should know from electronics that power is equal to voltage times current. So in this case, it will be 120 times 2, which is 240 watts. And, well, we just want the work itself done, so we just need to multiply this by the time that it's actually running. So we have 240 watts for 300 seconds, which gives us 72 kilojoules. Okay. Step 2, let's figure out by how much our internal energy changes. So delta U is equal to Q plus work other plus work PV. Now, in this case, we do have some Q, it's our heat loss. We have some other work, that's, as we've established, is the work being done by the heater. And we also have PV work because the piston is expanding. However, we know that delta H, the change in enthalpy, is equal to Q plus work PV, right? Wait, no, plus work other. So, let's start with this for now. This implies that mCp, because remember, constant pressure, delta T, is equal to Q plus work other by definition. Now, we need to figure out Cp. So, Cp is equal to F over 2 plus 1 times R. Well, nR, but let's do R over M. I mean, big M for the molar ratio to get it in kilograms Kelvin, joules per kilogram Kelvin. So first of all, we need to figure out our molar ratio. So let's go back to our periodic table over here. And we are dealing with nitrogen, which is over here. So we can see that it has a molar ratio of 14 grams per mole. So let's go ahead and go back to our notes. And here we are. So MR equals 28.1 grams per mole. And you might be wondering, but didn't you just say that it was about 14? Yes, I did say that it was 14, but that is for a single nitrogen atom. And you should also know this, nitrogen gas is actually diatomic, so it's written as N2. This means that our degrees of freedom is 5, but that also means that we have 2 nitrogen atoms, so 14 times 2 is 28, and if you do all the numbers, it's about 28.1. So that's why I've written 28.1 grams per mole, which is 28.1 times 10 to the minus 3 kilograms per mole. Okay, so now we can calculate CP. So CP will be 5 over 2 plus 1 times 8.314 divided by 28.1 times 10 to the minus 3, which gives you 1035.6 kilojoules per kilogram Kelvin. And the reason why we're dividing by, the molar ratio in the first place is because R, the ideal gas constant, is in kilojoules per mole Kelvin. But we're going to be dealing with kilograms because we were given, we were given a volume, and generally it's easier to work with kilograms than with moles, I think. So this makes it nice and easy. Okay, now we need to actually figure out how much mass we have. So we know that m is equal to n times our molar ratio. Okay, but what is n? Well, remember, PV equals nRT from our ideal gas law, which means that n is equal to PV over RT. So we get, if we calculate n, we have 80.146 mole. So we just need to multiply this 80.146 by our 28.1 times 10 to the 0.1 times 10 to the minus 3, which gives us about 2.25 kilograms. Okay, so now that we have our mass, we can go back to this equation over here, because now we have everything minus our final temperature to actually figure out what's going on. So let's write it down. mCp delta T equals Q plus work other. We know that delta T must be equal to Q plus work other divided by mCp. So it's just a case of plugging in the numbers. So we know that Q is our heat loss, which was minus 2,800 joules, plus the work that the electric heater did, which was 72 kilojoules. Oh, wait, I realized I made a mistake here. R was given in joules, not kilojoules, so watch out. So this is, in fact, just 1035 joules, not kilojoules, and we have a mass of 2.25. So plug in all the numbers into your calculator and you get 29.6 Kelvin. Now, that means that T final minus T initial must be equal to 29.6 Kelvin, which means that Tf must be equal to 29.6 plus our initial temperature of 300.15, which is 329.75 Kelvin, which, if you convert back to degrees, is 56.6 degrees Celsius. Next, electricity generation in a Stirling engine using hydrogen. Okay, so I'm gonna use a box to represent our engine here. I don't feel like drawing an actual engine. So let's just go with this. So we've got a stream of nitrogen coming in at 500 Kelvin with a flow of 2 grams per second. We also have a second flow of 300 Kelvin with 1 gram per second. We generate 100 watts of electrical power. Okay, so coming out of here, we have work electric, which is workflow, 100 watts. And we also, obviously, any gas coming in must also eventually come out. So we also have some flow. Let's number these to make life easier. 1, 2, and 3. So this flow will have some flow 3 with some temperature T3. So we can neglect kinetic and potential energy, that is nice. We can assume steady state, that is also very nice. And we can assume that heat transfer with surroundings is 0, and we are told that the heat capacity of nitrogen is this is the specific heat capacity in grams, so that means mass, so is 1.04 joules per grams per Kelvin. Let's start with our energy balance. So dE dt will be the sum of all the heat flows plus the sum of all the work flows plus any mass flows. We can neglect kinetic and potential energy, so that's just enthalpy, specific enthalpy with respect to mass going in, and any sum going out of mass flows times the enthalpies, because again we can ignore kinetic and potential energies. So step 1 is to realize that your two flows over here somewhere within your system eventually connect and they become one mass flow, which through the conservation of mass, because you know it can just disappear into thin air, means that your outflow M3 is equal to M1 plus M2, which is very nice. So this is simply 2 plus 1, which is 3 grams per second. Okay, so step 2 is to set up our force balance. Well, like replace all the stuff into the force balance. So we were told that it's a steady state, so it's not changing in energy. Well, the system isn't changing in energy as a whole. We know that our heat flow is 0 because we were told there's no heat flow to the surroundings, and any heat flow within the system we can sort of ignore. So our workflows, we only have one, and that is the electricity that we're taking out. So W flow, W dot elec. And our mass flows coming in, we have M dot 1 H1 plus M dot 2 H2 minus M dot 3 H3. So if we rearrange this a little bit, we get that minus W elec is equal to M1, why do I keep writing I, H1 plus M2 H2 minus M dot 3 H3. So now we can replace all these enthalpies. We are dealing with the same thing here, so the specific heat will be the same for all of them. So we are told that Cp is 1.04. Let's not substitute any numbers in for now. So we get minus W elec is equal to M1 times H1, which is Cp T1 plus M dot 2 Cp T2 minus M dot 3 T3. So let's rearrange this. So all the M1 and 2 stuff will be negative on the other side, and that leaves negative M3. So you divide everything by negative M3. So you get that T3 is equal, let me move it down. T3 is equal to M1 Cp T1 plus M.2 Cp T2 plus W elec divided by M.3. And here I'm missing a Cp. There we go. So yeah, now it's just a case of plugging in the numbers. So let's go ahead and do that. We have, I'm gonna add brackets here for clarity. So 2 times 1.04 times 500. So that's our first flow basically. Then we have 1 times 1.04 times 300, that's our second flow. Then our work is minus 100 watts because we are losing it. And then we have our third flow of 3 times 1.04. So you plug this into your calculator and you should get a number of 401.3 Kelvin. Which, going back to the thing, to the PDF, we seem to be 1 decimal point off once again. I'm probably using a rounding error somewhere. Oh, if you look at that, they gave us a nice little diagram. Well, I mean, it works either way. Let's go ahead and move on to problem 5. That is a terrible 5. So helium is to be compressed from 1 bar. Okay, let's write this all down. So P1 is 1.05 bar. T1 is 295 Kelvin. And then we have P2 equals 7 bar. And T2 equals 460 Kelvin. We have a heat loss of 15 kilojoules per kilogram. Okay, so let's make this small q loss. This means specific heat. Well, not specific heat, specific heat loss with respect to mass. So this was minus 15 kilojoules, yes, kilojoules. Again, the minus is because we are losing this energy. We also have a, we can neglect kinetic energy changes. I guess they also mean potential energy changes. We need to find the power in order to achieve a flow rate of 60 kilograms per minute. Okay, so our target is 60 kilograms per minute, which if you divide by 60, you get 1 kilogram per second. Okay, helium is an ideal gas with 3 degrees of freedom. Okay, that's nice, so F equals 3. And we can consider it an ideal gas. And we were told the molar ratio, which is nice. We don't need to look it up in our table, even though we know already from the earlier question that it's 4 grams per mole. So we can assume steady state as well. Okay, that's nice. So steady. All right. Let's start by calculating our heat capacity. So Cp is equal to Cv plus R over mR, because remember we want this with respect, we want the specific heat capacity with respect to mass. So this simplifies to F over 2 plus 1 R over mR, which if we plug in the numbers, we get 3 over 2 plus 1 times 8.31 over 4 times 10 to the minus 3. Did I not write it down? I seem to not have written it down. 4 times 10 to the minus 3 kilograms per mole. Yeah. So you plug in all those numbers and you get a very nice 5,196.3 joules per kilogram Kelvin. So this is our specific heat capacity, and let's go ahead and set up our force balance, or the energy balance. dt is the sum of heat flows plus the sum of work flows plus the sum of mass flows going in. We can ignore the energy, so just enthalpy, minus the flows going out. So we were given here our Q in energy per mass, per unit mass, so in this case kilograms. So let's go ahead and work with that. So steady state means that energy is not changing, so it's 0. We are doing this in per unit mass, so we can just directly write in our Q loss. Let's do small w, stick consistent with our work in, which is the thing we're trying to figure out. And if we divide mh by m, we obviously only get h, so we get h in minus h out. So this means that our W in is equal to our H out minus the H in minus the Q loss. So if we start substituting this in, this is, remember this is per unit mass, so we leave out the mass, Cp delta T minus Q loss, right? Because the only difference between the two are the two temperatures. Let's just fill in the values. So Cp is 5196.3. Our two temperatures are 460 minus 295. And we need to subtract our loss, which was 15 kilojoules. And just so you don't get confused, this has units of joules per kilogram because we're working in, energy per unit mass. So this works out to 872.39 kilojoules per kilogram. And now the final step is figuring out our actual work. So our actual work, which we need to, or our power which we need to put in, will be our mass flow times our work per unit mass. And what you should realize is that the mass flow in and the mass flow out are the same because you only have one thing coming in and one thing coming out, and the mass cannot magically disappear inside. So we have a target of 1 kilogram per second, so that's just 1 times W in, which is 872.4 kilojoules per second, which is 872.4 kilowatts, which is slightly off from the PDF, but again, rounding error somewhere. The procedure is what's important here, I think. So problem number 6, the heat exchanger. So we have a pipe over here. This is the pipe wall. Let's go like this. And then we've got a tube, presumably, which I suppose is the same as a pipe, running through the other one, but they are not connected. This is important. They are not connected, which means there is no mass exchange between system 1, which, let's outline it in blue. So this is system 1, and we've got a second system over here. What is that? We've got a second system over here. And these two do not exchange mass between one another. So there can be a heat exchange between the orange and the blue system, but there is no mass exchange between the two, and that is important. There's also no work exchange between the two. It's not like there's a shaft running from one to the other. It's just heat flows. Let's see, what do we have? We have that nitrogen with a flow rate of 1 gram per second. So here we've got nitrogen coming in at 1 gram per second. It comes in with 60 degrees C, and it should be cooled down to 30 degrees C. We also have water entering here at 20 degrees C and leaving at 25 degrees C. We are given the heat capacity of nitrogen, let's call this CPN, 1.040 kilojoules per kilogram Kelvin, and we are also given the specific heat capacity of water. I'm going to go with W, which is a 4.186 kilojoules per kilogram Kelvin. So we need to determine the mass flow rate of the water and B, the energy that's actually absorbed by the water. Okay, for problems like this, it's the easiest thing you can do is work with the enthalpies. Basically, your mass flow going into, like if we just focus on the blue system, your mass flow going into the pipe is also the exact same mass flow flowing out of the pipe. which means that if we look at our energy balance, we established already that there can be a heat flow, but there is no work flow. So our energy, well, let me write it down. So our heat balance always looks like this, you know, all the heat flows and then all the work flows, and then all the mass flows. This is in, and minus the ones going out. Here I am also ignoring potential and kinetic energies, but I mean, you can just pretend that they are there. Here, there's a couple things to realize. You could take the entire heat exchanger as a thing. However, you would not be able to see the heat exchange happening between the blue subsystem and the orange subsystem, because essentially all the energy within the system wouldn't change. So that's why we need to divide the system, you know, the entire heat exchanger, into the two subsystems, the blue one with the nitrogen and the orange one with the water, in order to see some sort of change. And like I said, the easiest way to approach this is with the enthalpies. So the enthalpy of the nitrogen should be equal to the enthalpy of the water. Well, the change in enthalpy, at least. So let's go ahead and write that. The change in enthalpy for the nitrogen should be equal to the change in enthalpy of the water. Why is that? Well, you can imagine looking at our energy balance above. If you just focus on the bit with the mass flows, the mass flow going into the pipe is the same as the one coming out of the pipe, which means that your only difference is the enthalpy between the entrance of the pipe and the outside of the pipe for each subsystem. So that's your delta H. And this energy has to go somewhere. And the only place it can go, if we look not at the two subsystems, but at the whole system as a whole, well, the only place where the energy from the blue system can flow is into the orange one, and vice versa. So that's why we can say that the enthalpies of both, the change in enthalpies of both systems has to be equal to each other. So now we just replace it with our m dot n c p n T1 minus T2. Let's go ahead and label this. This is area 1, area 2, area 3, area 4. T1 minus T2, and it just makes, you know, numbering or writing things down easier. So then we have the mass flow of the water, Cp water, times T4 minus T3. And here you might be asking yourself, well, why here did you take the entering temperature minus the exit temperature, and then in this section you did the opposite, you did the exit temperature minus the entering temperature? And the reason for this is because if you think about it, if you've got energy flowing from one system to the other, then that means that the energy flowing into the other system is the exact same. So it's mathematically, it has the opposing sign. So you can imagine that this minus this has to be equal to 0. So this minus here basically flips the two temperatures around, because these two numbers should be positive, and obviously if you do 30 minus 60 you would get a negative number, but no, here both numbers should be positive, so that's why we do that. And now it's just a case of plugging in the number, so we have 1 times 1.040 times 60 minus 30, and here you're asking, oh, but why didn't you convert to Kelvin? Well, if you're just gonna be adding 273.15 to each number, then subtracting the two numbers, the difference will be exactly the same as if you just keep it in Celsius for now, because the conversion is linear, which means that the subtraction will also be exactly the same. So that's why we can keep just the Celsius. And here we have our unknown. This is what we're trying to figure out. And times 4.186 times 25 minus 20. If you plug these numbers into your calculator, you should get 31.2 grams per second times kilojoules per kilogram. The reason it has such weird units is because here I didn't convert to kilograms, but don't worry about it, we don't really need to do that for now. And we get this times 20.93 kilojoules per kilogram. And the reason I didn't convert to kilograms over here is because if you notice, here, this unit, to get MW, we need to divide both sides by this, and that means as this has the same units as this, they will cancel out, which will just leave you with grams per second, which is a perfectly usable unit for the mass flow, and it has the advantage that we don't need to do any conversions. So that means that MW is equal to 31.2 over 20.93, which is 1.49 grams per second. Which, if we go back to our tutorial PDF, we can see is indeed the correct answer. So now we can move on to part B, in which we need to actually find the actual amount of energy that gets transferred to the water. So, like I mentioned before, for the blue system, we know everything. We know both temperatures, we know the mass flow, we know the temperatures, and we know the specific heat, which means we can calculate the enthalpy. And now we also have the mass flow for the orange system, which means we can also do everything with that one. And as we know, delta H is equal to Q plus work other. However, in this case, there is no work being done by one system on the other. It is pure mass flows, which means that in reality, our enthalpy is just our mass. Our change in enthalpy is just our heat flow. And that is very nice, because that means that our heat flow is equal to M of the water times Cp water times delta T. And we now have all these numbers, so we can just go ahead and plug them in. So 1.49. Here we do need to convert times 4.186 times 25 minus 20, and if you plug this all into your calculator, you get 31.2 kilowatts. Now, you might be asking, but wait, the answer sheet says, or the PDF says, 31.2 watts. Why did we get 31.2 kilowatts? And, well, the reason for that is because we were given the specific heat capacities in kilojoules, not joules. If you work with the units over here, so if we take this blue section over here and we actually write down our units, we have kilograms per second being multiplied by kilojoules per kilogram times Kelvin being multiplied by Kelvin. So here Kelvins cancel out, kilograms cancel out, which leaves you with kilojoules per second, which is the same as kilowatts. So this is probably just a typo. if you just change the heat capacities from kilojoules to joules, obviously keeping the number the same, you do get 31.2 watts instead of kilowatts. And because this discrepancy comes from the specific heat capacities, you don't actually see it in part A. So in part A, you do still get that 1.49 grams per second, but in part B, you do see the discrepancy. But yeah, I wouldn't worry about it. The procedure is correct. So now it's time to move on to our, to my group's extra problem. So this was also about a heat exchanger. Now, the professor did ask us to not take any pictures, so I will be just drawing my own from what I can remember. The problem was basically you have two loops. So here, let's say this is loop 1. And let's just mirror this horizontally. This is your second loop. So within these two loops, you've got water running. So here, this was like your primary loop, and this was your tap water loop. So here, your tap water enters with a cold temperature, and it comes out warm. And then here, it's the opposite. To be honest, I don't know if the flow was indicated, but the point is it enters warm, and exits cold. And we were given some numbers. So unfortunately, in real life, nothing is perfect. So we do have a bit of heat loss during this process, but we can assume steady flow, a steady state. So you can imagine these two loops are constantly running, which means you have a nice constant flow coming in and out of these heat exchangers over here. And we were also told that we could ignore potential and kinetic energies, which is nice. So we were given some data, T1. So let's say 1, 2, 3, 4. So we were given T1 was 90 degrees, T2 is 70 degrees, T3 is 15 degrees, and T4 is 50 degrees. So basically here in your primary loop, you've got water coming in hot and leaving a bit colder, and then in your secondary tap water loop, you've got cold water coming in and leaving in hot. We were also given flow rates. So here your primary loop has a flow rate of 4 grams per second with a specific heat capacity of 4 joules per gram Kelvin. This is MP. And here our tap flow was unknown, and we had a specific heat capacity of 4.2 joules per gram Kelvin. Now you will notice that here the units are in grams and joules, which is different than your usual kilojoules and kilograms, but as they are the same sort of units, we don't need to do any conversions, so that is nice. And we were also told that this Q loss was 20 watts. And as it's in watts, it's actually a heat flow, which we are losing. So again, for this type of problem, the easiest thing to do is to work with enthalpies. So you know that your change in enthalpy of your primary loop will be the heat flow plus your other work. But again, between the two heat exchangers, there is no work being done, there's only heat. So in this case, this will be our Q loss plus, let's make this minus 20 because, you know, we are losing it, plus, yeah, the flow from 1 to 2. So from, okay, let's be consistent, from the primary loop to the tap loop. And we also know that our enthalpy is mCp delta T. And what's nice is we have all this data. So we just plug in the numbers, 4 times 4 times 970 minus 90, and is equal to Q loss plus Q P2 tap. So if you plug in the numbers on the left side, you get minus 320 joules, which makes sense because that energy is moving out of your system into the other loop. And we've got minus 20 plus Q from P to the tap loop. So if we just rearrange this, you get that your heat flow from the primary loop to the tap loop is equal to 300 joules. 300 watts. It's a heat flow, so it's in watts. This is in watts. So now we know how much energy has gone from this loop into that loop, which means we can do the same. So the change in enthalpy for the tap loop will be the same as the heat flow from the primary loop to the tap loop, which is 300 watts. And this has to be equal to our mystery tap flow times 4.2 times the changes in temperature, which in this case is 50 minus 15. And again, like in the previous problem, I'm not converting to Kelvin because the temperature difference is the same whether you leave it in Celsius or in Kelvin. So if you plug in your numbers here, you get that your mass flow should be 300 watts divided by 4.2 times 50 minus 15 is 35, I believe, which gives you 2.04 grams per second. And this is the correct answer. So yeah, basically whenever you have a heat exchanger problem, the easiest thing to do is to just work with the enthalpies, because if you look at your system as a whole, um, there is no energy change, which means in order to see an energy change, you need to subdivide it. And as soon as you do that, the energy flowing from one subsystem can only flow into your other subsystem, unless you've got, some losses, but those are very easy to account for. You just, add them there. And if these two things are mechanically separated, so if there's no like electrical circuits going between the two, or like shafts with pedals or gears or whatever, if it's just two passive elements, basically two metal blocks touching each other essentially, or two pipes, your enthalpy will only be a heat flow. And that makes things a lot easier, because as long as you have all the data for one subsystem, you can figure out your second subsystem.